In this section, we're going to look at another multiplication rule for probability. So this is again where we have two separate events. I want this event to happen and I want that event to happen, and we're supposed to multiply. But in this situation, the first event is going to affect the second event. And so we're going to have what's called conditional probabilities because our events are going to be dependent on each other this time. So let's kind of use some examples from what we would have seen last time with independent events. So for example, the probability that I toss a head on a coin and then I roll a 4 on a 6-sided die. Now we had said before that events like this would be independent. When I go to toss a coin and let's say I get a heads, that event has no bearing on what happens when I go to roll my die and I get a 4. That die has no idea what happened when I tossed that coin, so getting a head in no way affects rolling my die and getting a 4. And so this is just straight up turning into multiplication. So I take the probability that I toss a head and I multiply that, remember and turns into multiplication, multiply that by the probability that I roll a 4 on the die. Again, tossing a head and rolling a 4, totally independent, one didn't affect the other. And so I'm just turning it into multiplication. So when I toss a head, there's only one head on the coin out of two sides of the coin. So I get 1/2 for the probability of tossing a head, and then rolling a 4, there's only one 4 on a 6-sided die, and again there are 6 sides, so 1 out of 6. And I multiply fractions straight across, so that should give me 1/12. And if I go to my calculator and I divide 1 divided by 12, I get a decimal. And remember, for our class, we're going to go ahead and round all of our probabilities to 4 places. So I would round that to 0.0833. So again, I'm showing how my formula applies. The and turns into multiplication. I show what each of my probabilities are, I multiply them together, and I round my answer to 4 places. So another example of this and that happening, let's say I'm drawing cards from a deck. Let's say I draw an ace and then I draw a king. And last time we got really specific about what happens when I draw that first card and it's an ace. So let's say I draw that card, I see it's an ace, and then I tuck it back into the deck. And I reshuffle and I draw another card and I want to know what's the probability that that second one's a king. So what we saw last time was, again, the and turns into multiplication. So I've got the probability that I draw an ace times the probability that I draw a king. And again, there are 4 aces in a deck of 52 cards. And I'm assuming that that ace, once it's been drawn, it gets tucked back into that deck, reshuffled, and now I go to draw my second card. There are 4 kings in a deck, and again, 52 cards in the whole deck. And if I multiply straight across, I get 4 times 4 is 16 on top. On bottom, I've got 52 times 52 is 2704. So when I do my division to get my decimal, that'll round to 0.0059. And again, when we treated this problem in the way that we did, this is like what we did last time, where the and turned to multiplication. We were saying we drew a card, it's an ace, tuck it back into the deck, reshuffle it, and that deck's the same deck as it was originally. I go to draw my second card, hoping for a king. But what if I didn't tuck that ace back into the deck? What if when I drew the ace, I hid it in my pocket? And now I've got a new deck, the conditions have changed. My deck now has only 51 cards, it's short an ace. That ace is in my pocket now. And I've only got 51 cards in the deck, and now the likelihood that I draw a king, it's different now because I have different conditions. And so this is what we would call a conditional probability, and the rules are different. So this was all when we had independent events, but let's look at what happens with dependent events. Dependent events where the first event happening changes the likelihood of the second. So we've got a general multiplication rule. This rule is going to be good whether events are dependent or independent. So the general multiplication rule for probability. We'll say if I have the probability of some event E and then some event F happening, that's going to be the probability of the first event happening times, and so far this looks like the exact same rule as we had before, but here's where it changes. Instead of just multiplying by the probability of that second event happening, since the likelihood of the second event is now different because the first thing has happened, I have a conditional probability, and so here's the notation that I use. I have this vertical bar here that basically says, given that. And so the way I would read this is that this is the probability that this second event F happens, given that the event E has already occurred. And the event E occurring changes things because these might be dependent events where E changes the likelihood of F. So it looks very similar to the previous formula. The previous formula stopped here and said probability of F happening, period. But now I'm saying, well, what if E has already happened? So given that E has already happened, what's the probability of F happening? It should be different for our dependent events. So let's look at that example again, where we were looking at the probability that we draw an ace and we draw a king. Let's look at that probability one more time, and let's imagine that the conditions are a little different. This time I draw a card, I look at it and I say, ooh, it's an ace. Okay, I'm gonna put it in my pocket, and now my deck's different. It only has the 51 cards, and now I'm gonna go draw my second card from that. So now things have changed. Still the word and means multiply. So that's still the general rule. And turns into multiplication. But I'm gonna be looking at the probability that I draw an ace. That part's the same. And turns into times. And I do want to look at the probability that I draw a king, but I want to look at it in such a way that I have assumed, or given that, I have already drawn an ace. So I'm going to draw an ace first, tuck it in my pocket, and now with this new deck I'm going to draw a king, given that I've already drawn an ace and it's been thrown out. So now, to draw an ace in the first place, like we saw before, there are 4 aces out of 52 cards in a deck. So that part's still the same. It always starts the same. But it's this second part that's different. That vertical bar, again, that given that statement, this is a conditional probability, meaning things have changed. When that first event happened, things have now changed. So now I want to look at what's the probability that I get a king if the ace has already been drawn and tucked away. So let's think about that new deck. If I draw an ace and I tuck it away, we said there's only 51 cards left in the deck. How many of those are kings? Well, if the one I drew was an ace and I tucked it away, there's still 4 kings in the deck. And same as before, I'm going to multiply straight across. The 4 times 4 gives me 16. But now I have a 52 times a 51, which is 2652. Different than the 2704 we had before. And so when I get my decimal approximation, it's 0.0060. The chances are ever so slightly higher than it was if I didn't replace, or if I did replace that card. So again, this vertical bar is all about conditional probability, assuming that things have changed. So I did this first event, and now I'm changing the deck by tucking that card back in my pocket, and my deck is now different and only has the 51 cards. So let's kind of stick with this card idea and look at a few other conditional probabilities just with the cards while we're thinking about it, and then we'll pull out some examples from the book to look at. So let's look at the probability that I draw the Queen of Hearts, and then I draw, what do I want to do? Draw a heart. And I'm going to start kind of truncating this with some symbols instead of writing it all out. But again, the key word here that we want to highlight is that word and always means we're going to multiply. But let's go into this one assuming that I'm not replacing the card. So I'm going to draw my first card, hoping it's a Queen of Hearts. Whatever it is, I'm tucking it in my back pocket, and now my deck is different. So to find this probability, I take the probability of the first event, so that I draw the Queen of Hearts. I always start with that first event, and then and turns into multiply, and this is where things change. Now I want to know the likelihood that I draw a heart, given that I've already drawn the Queen of Hearts. So let's see how this one plays out. Going for my first event, what's the likelihood that it's the Queen of Hearts? Well, in that initial deck, there are 52 cards. We started with a standard deck, and there's only one Queen of Hearts in the deck. So 1 out of 52 is the chances of getting a Queen of Hearts to start with. So now let's assume I've got that, and I put it in my back pocket, and now my deck is different. Given that I've already drawn the Queen of Hearts, how many cards are left in the deck? There should only be 51. So 51 cards left in the deck. How many of them were hearts? Well, I drew the Queen of Hearts, which is one of them, and I tucked it away, so there should only be 12 more hearts left. There's 13 hearts in the whole deck, but if I drew the Queen of Hearts and tucked it away, there's only 12 more. So again, multiplying straight across, we get a 12 on top. We get a 2652 in our denominator here. And so when I divide and get my decimal rounded to 4 places, we're looking at 0.0045. So again, big picture is that and is turning into multiplication. The first event, you basically just bring it straight down. It's the second event that is conditional upon the first event having already happened. So the first part always is standard and kind of the same as what we've been doing. It's this second piece that changes. All right, let's look at another one. Let's look at the probability that I draw a club and then I draw a black card. Again, the key word is and. It means we're going to be multiplying at some point. First part always stays the same, so probability that I'm going to draw a club. And then and turns to times. It's the second piece that's now different. It's dependent on what first happened. So I'm going to look at the probability that I draw a black. But I'm looking at that probability given that I've already drawn a club. So I go to draw my card out of a standard deck of 52. It happens to be a club. I put it in my pocket. Now I look at my new deck of 51. That's where I get this probability. So to start with, we had that standard deck of 52 cards. How many of those are clubs? There's 13 of them. So that's a quarter of the deck, 13 clubs. So now times, again, and turns to times. If I've drawn that club and I put it in my back pocket, there are now 51 cards left in the deck. How many of them are black? Well, if I drew the first card and it's a club, which is a black card, I put it in my pocket, there are originally 26 black cards in the deck, and if I took one of them and put it in my pocket, now there's only 25 left. So there's 25 black cards left. And again, we want to multiply everything straight across. So we got 13 times 25, which is 325. And then on bottom, we got that 2652 again, which is a decimal. Looks like 0.1225. So again, big picture and turns into times. The first part stays kind of the same as what we're used to. It's the second part that is conditional upon the first thing already having had happened. All right, so now let's look at an example from the book that's not just card stuff, so you don't have to know your standard deck of 52 cards to be able to do this one. This is going to be, let's see, which one do I want to do? Let's do number 30. So this is page 272, number 30. And this one's involving golf balls. So we've got 35 experienced golf balls in this bag, and we've got 20 that are Titleist. Oops. Titleist. We've got 8 that are Maxi Flies, or Max Flies. Max Flies, and then 7 Top Flights. All right, so we've got several different parts to this problem. The first part, so part A, they want us to find the probability that 2 randomly selected golf balls happen to both be Titleists. So probability that you get 2 Titleists. So the way I'll write this is I'll say, what's the probability that when I grab a ball out of the bag, the first one I get is a Titleist, and the second ball I grab is another Titleist. So when they say you're getting 2 balls out of this onion bag, and they both are Titleists, I'm just going to say the first one's a Titleist, and the second one's also a Titleist. And so that and is going to turn into multiplication. So I've got the probability that the first golf ball is a Titleist. But then the idea is I'm not taking the golf ball and then putting it back in and then grabbing another one. I'm supposed to be taking 2 balls out of the bag. And so in theory, you can think of it as I take a ball and I hold on to it, and then I go to grab my second one so that I've got 2 out of the bag. So if I take the first golf ball and it's a Titleist and then I hold on to it, now when I go to grab the second golf ball, the bag looks different than it started. So I want to now know what's the likelihood or the probability that my second golf ball is a Titleist, given that I've already got a Titleist from the bag when I grab the first one. And so this is where the notation can kind of get a little confusing when you go back to look at it. So here's how I would do this just kind of for myself when I'm reading it. This is the first ball that I grab out of the bag. It happens to be a Titleist. That's always the first guy. And now I'm multiplying it by the probability that the second ball I grab is also a Titleist, given that the first ball I grabbed out of the bag was a Titleist to begin with. So first ball is always the first one you mention, and then here's the second one, given that the first one was the Titleist. So now let's go and look at the probabilities. So I want to know what's the likelihood of grabbing a Titleist ball out of the bag. And in this bag, it looks like we got 35 golf balls all together. And how many of them were Titleists? There were 20. So there's the probability of getting a Titleist out of that bag first and foremost. Now assume that that first golf ball is in fact a Titleist. Now you're going to hold on to it. And then we go reach in to grab another one. At this point, there are only 34 golf balls left in the bag because I took one out. So there's 34 balls left, and how many of those that are left are Titleists? Well, I had 20 originally, but I kept one when I grabbed it out of the bag. So there should only be 19 left. And then again, I want to multiply straight across. So we got the 20 times the 19, we get 380. And then denominator, we got 30, whoops, wrong button. 35 times 34, we've got 1190. And so when I divide, I get a decimal of 0.3193. So what's the likelihood that we happen to grab 2 balls out of the bag and they're both Titleists, and the way we're thinking of it is you grab one, it's a Titleist, and then you go to grab a second one, it's also a Titleist. So I'm thinking of it in terms of the word and. And turns into multiplication. I multiply the first event happening to the second event happening, given that the first already did. And again, that second fraction or that second probability is conditional, so it's a little different than what we started with. And as always, we multiply straight across and go for that decimal answer. All right, let's look at the next one. Let's look at part B. All right, part B. What's the probability that the first ball is a Titleist, the second one is a max fly? So we get a Titleist first, and then we get a max fly second. So again, the word and implies we're going to be doing multiplication, always starting with the first event. So probability that I have a ball that I grab that's a Titleist and turns to times. And if I'm assuming, again, I'm grabbing the first ball, keeping it, grabbing the second one, and then hanging on to that, the first one that I grab is a Titleist, hold on to it. When I go to grab the second one, things have changed. So I want to know what's the likelihood that second ball is a max fly, given that I've already taken a Titleist out of the bag. So again, if you want to notate this, this is the first ball picked out of the bag, and then here's the second one, given that the first one was already drawn. So when I go to grab the first ball, there are again 35 balls in the bag, and of those 35, there were 20 Titleists. So there's my probability of getting a Titleist first. But again, when I grab that Titleist out of the bag, now I hang on to it, and there's only 34 balls left in the bag. Of those 34, how many are max flies? Well, they're all still there because I didn't take one out. I took a Titleist out. So there's still 8 max flies in the bag. And again, when I multiply straight across, the 20 times 8 should give me 160. The 35 times 34 gives me the 1190. And then when I divide, whoa, that's not right. 160 divided by 1190. When I divide, I get 0.134, and then I'm going to round to a 5 there. All right, so again, the big picture for all of this, and is going to turn into multiplication, but because I'm taking 2 balls out of the bag at once, or in essence taking one, hanging onto it, and grabbing another one, there is a conditional probability idea happening. So the likelihood that the second ball looks like this, given that the first one was that one. Let's see. Now the next example, part C, basically what part C is having us do is switch these around. Now they're saying, well, what if the first ball's a max fly and then the second one is a Titleist? And all that's going to change is this is going to turn into max fly, this is going to turn into Titleist, and this will turn into max fly. They'll all switch around because the order's going to switch. But what's going to happen is this is all going to be the same, because it all comes down to multiplication. If you change the order of multiplication, you get the same thing. So let's see that that actually works. So I'm going to do max fly and Titleist and see how that changes things. So max fly first and Titleist second. Again, that key word is and it turns into multiplication. So I'm looking at the probability that the first ball I take out of the bag is a max fly times the probability that the second ball is a Titleist, given that the first one was a max fly to begin with. So again, if you want, you can say this was the first ball taken from the bag, here's the second one, given that the first one was already drawn. So in the original bag, there were 35 balls altogether, and if the first ball was a max fly, there were 8 of those in the bag of 35. Times, Now if I take that max fly and hang on to it, there's only 34 golf balls left in the bag. And the first one I picked was a max fly. There's still 20 Titleists left in the bag. There's still 20. And so again, you'll see the same probability we had before, the 8 times 20, that's the same as 20 times 8, so that'll be the 160 again. And then the 35 times 34, again, is the 1190. And so we still get the probability 0.1345 when you round. And that, whoops, that was part C. Hollow. That's part C. Now part D says, what if you drew 2 balls and you didn't really pay attention to which was first or which was second, you just said, hey, I've got 2, and I want one to be a max fly and one to be a Titleist, but it doesn't really matter which order. What that would be saying is that you want to know the probability that you get a max fly and a Titleist, or a Titleist and a max fly. What that's saying is I don't care what order. It'd be fine if it was max fly first and then Titleist second, or it would be fine if it was Titleist first and max fly second. And we already found this probability, this and probability, it's right up here. We already found this and probability, and we found it to be the same answer. So now or, we saw several lessons ago, or turns into addition. So if I want that probability or this one, I'm taking this number that I got for each of these, and I'm adding it to itself. So really for part D, you'd just be taking this number and you'd be doubling it. That's all you'd be doing. All right, so we're gonna look at another example. So this one's gonna be from page 273, number 36, and this one looks like we got a random sample of registered voters, and there's a table here . So one big thing that we want to be able to get out of tables is how can we understand conditional probabilities when everything's presented in a table and it's not just kind of in theory, if I drew this card and then didn't put it back, how many are left and that sort of thing. So the big thing to remember with conditional probability when you're reading it from a table is that whenever they say given that, think of it as assuming that. So given that or assuming that, what it's going to have me do is kind of narrow my vision in the table here. So let's see, where are we eventually going to be going? In part A, they're referring to Republicans, which is this row, and they're referring to ages 30 through 44, which is this row. So I just want to look at those two places to kind of say a for instance. So let's say, for instance, what's the probability that someone's Republican? Let's just start there. So the probability that someone's Republican, what we'd do is we'd say, well, how many Republicans are there altogether? There are 2,200 Republicans. Out of how many people are there altogether? 4,000. And so my decimal would be 0.55. So that's the probability of being a Republican in general. Let's look at the probability that someone is aged 30 through 44. So I want to know how many people are in this age group. Altogether there are 724 of them out of 4,000 people total. And so my decimal would be 0.181. Now the nice thing about the tables is that we can find and or kind of more quickly than we can with using the formulas that we've seen before. So for example, if I wanted to know what's the probability that someone is Republican and is in the age group 30 to 44, really when it comes to the table, I'm looking for an intersection between Republicans, which is this row, and ages 30 through 44, which is this column. And if I look at where those intersect, they intersect right here at 340. There are only 340 people who are Republican and in that age category at the same time. And so in terms of the and, there's 340 people out of the 4,000 who are Republican and in that age group at the same time. So when I look at that decimal, oh, fingers, start working. 0.085. And if I wanted to do or, so let's say, I'm gonna run out of room, Republican or 30 through 44 years old. That means I'd be okay if somebody was in this row, because that's Republican. I'm okay if someone's in this column, because that's the age group I'm after. And it's okay if they're both, meaning if they're in this area. So basically I'm adding up any of the cells that would represent either a Republican or 30 through 44 or both simultaneously. So I'm going to take the 224 because that's Republican. I'm going to take the 340 because it's both Republican and the right age group. I'll take the 1075 because that's Republican. I'll take the 561 because that's Republican. I'm not going to take the total because that's actually just adding all these up. But I'm taking each of those different numbers. Those are all the Republicans. And now when I look at these age groups, I'm not going to count him because I technically already did. He was counted when I counted all the Republicans. So I'm not going to count him again. But I will count the 384 because that was also in my age category. So if I take again the 224, which is a Republican, plus the 340, which was both, plus the 1075, which was Republican, plus the 561, which was Republican. So that's all the Republicans, is these four guys. And I've already got this for the 30 to 44, the 340, but I need the 384. Oops, plus 384. And when I add all of those up, I get a total of 2584 out of the 4,000 people. Oh dear. So that gives me a decimal of 0.646, and so that's the or. So to find Republicans, you add up all the Republicans, divide by how many there are. To find the probability of this age group, you find out how many are in that age group, divide by how many there are. To do the and, that's the intersection, divide by how many there are. To do the or, you add up all the individual guys, divide by how many there are. So that kind of is like a review of what we've seen with the tables before, but now we're going to look at what happens with conditional probabilities. So let's consider the probability that someone is Republican, given that we know them to be between 30 and 44 years old. So again, that vertical bar means given that, or assuming that, or in this case, I'm going to say kind of put on some blinders and just kind of only look at the thing that's given, the thing that's assumed, the thing that we already know to be true. Given that this is true, how many Republicans are in there? So when I see a given that statement in a table, really what I'm doing is I'm isolating my vision to the thing that is given. So if it's given that someone is between 30 and 44 years old, the idea is that my vision is getting narrowed to just that idea. Just the guys who are between 30 and 44 years old, because that's the given, that's what's assumed, that's what we know to be true. So don't look at anything else. I'm not looking at people who are that young. I'm not looking at people in this age range. I'm only looking for this age range. That's the only thing that I know that's given, that's assumed. So let's just look there and ignore everything else. Given that this is what I'm looking at, what's the likelihood someone is a Republican? Well, that's going to be how many Republicans are in this area. There's 340 of them. And how many people are in that area. It's not the 4,000, because that was looking at a bunch of other stuff I didn't want to know. I want to assume this is all I'm looking at. So the only number of people in here is the 724. So given that I only look at this age group here, the probability someone's a Republican is 340 out of only 724. And that's different. Where did my black pen go? That's different when I found the probability of a Republican in general. In general, there were 2,200 Republicans out of 4,000. So if I know nothing about a person's age, I would guess the probability that someone's a Republican is this fraction, which as a decimal, let's get this decimal here. 2,200 divided by 4,000. So we had said that was 0.55. If I knew nothing about a person, the likelihood that they're a Republican is about 55% in this particular district. But if I happen to know their age is between 30 and 44 years old, then my probability is different. It changes. Now it's only 0.4696 when I round to 4 places, so it goes down. So if I know nothing about a person, the probability they're a Republican is about 55%. If I happen to know they're between 30 and 44, the chance that they're a Republican actually goes down. The fact that this changes things, the fact that knowing this condition, the fact that that changed the probability of someone being a Republican, knowing that condition, the fact that these are now different, it means they must have been dependent on each other. So the age category and this political affiliation, they're dependent on one another. When I know that this has happened, it changes the conditions. It changes the probability to something different. So for part A, when they're asking you, how do they say it? Part A, they say, are the events Republican, which is this row, and 30 to 44 years old, which is this column, are those independent? I would say, no, they're not. And it says to justify your answer, well, here again, if I know nothing about a person, the probability they're a Republican is this amount. If I happen to know that they're this age, the probability that they're a Republican changes. The fact that it's changed means that it was dependent. So your political affiliation of Republican depended on knowing your age. If the age was known, it changed the probability. So for the rest of the of number 36, you'll see part B is going to ask the same thing, but this time about Democrat and a different age category, and it wants to know, are they dependent or are they independent? So again, you'd be looking at, well, what's the probability that someone's a Democrat? And then say, well, what's the probability that they're a Democrat if I know that they're 65 and older? If it's different, knowing the age versus not knowing it, if it changes things, that's the conditional probability. Again, we'd say that they must be dependent on each other. If they're the same, we'd call them independent. And knowing the age didn't impact the political affiliation probability. So if you can know something and it doesn't change probabilities, then they're independent. But if it does change things to know some extra piece of information, if that changes things, they're dependent on each other. And then for parts C and D, they're asking about categories and whether they're mutually exclusive or not. So part C wants to know if this age category, 17 through 29, and this age category, 45 through 64, are those mutually exclusive? And basically all that's asking is there an overlap or not? And I can see that the people that are over here and the people that are over here, they're completely separated. There is no overlap, they are mutually exclusive. Whereas in part D, they want to know, is Republican, which is this row, and the age 45 through 64, which is this column, are those mutually exclusive? And the answer to that is no, because I can see a place where those categories cross or intersect or overlap. And since there is a place where they share something in common, that's that overlap of the Venn diagrams, they are not mutually exclusive. All right, so again, the big picture with all this stuff, not so much with the table, but with the general multiplication rule. If you see the word and you want to know that this happens and that happens, you're doing multiplication, and you have to ask, are they independent or not? If they're independent, first event has no bearing or no effect on the second event, just multiply them together. But if the first event changes things and it makes the likelihood of the second event different, then we have a conditional probability. And you can again see here the idea of the conditional probabilities. We're saying, okay, assume that that has already happened. In this case, assume that I know this information here and everything else is irrelevant. Assuming this to be true, now what's the probability? It's different, it's conditional.